Welcome back. This is Mr. Hyper taking you through still phase equilibrium, and today we are going to look at two component systems. In our previous videos, we were looking at one component system where we looked at water system, carbon dioxide system, and sulfur system. But this time, we are going to look at two component systems. And we are going to look at liquid equilibrium mixtures where we shall be having liquids involved. Then after this, after liquid mixtures, we shall be looking at solid liquid equilibrium mixtures or the eutectic mixtures. But before we go to eutectic mixtures, I found it wise to begin with this so that we move from this one to the other one. Now, liquid equilibrium mixtures. Now, you need to know that when two liquids do not react chemically, when two liquids that don't react chemically are mixed together, all right, there is formation of either miscible or immiscible liquid mixture, all right? Get two liquids which don't react chemically, mix them. You will either form a miscible or an immiscible liquid mixtures. Let me note that it is very important to note when two liquids which do not react chemically are mixed. Let me use the word are mixed. There is formation of either a miscible liquid mixture or an immiscible liquid mixture. We can either form a miscible or unmiscible liquid mixture. Now, let's begin with the miscible liquid mixtures. When we talk of miscible liquid mixtures, these ones are formed, right? When liquids completely dissolve in each other in any proportion to give a homogeneous solution, okay? Let me see, these are formed. Of course, we have said that these ones are formed when the liquids miscible liquid mixtures. These are formed when or they are liquid mixtures formed when liquids dissolve in each other completely, and say dissolve when liquids completely dissolve in each other, completely dissolve in each other in any proportion in any proportion to give a homogeneous solution. Homogeneous solution. Homo means the same, so they dissolve to form a uniform solution. It's like when you mix like water and milk. At the end of it all, you may not tell whether this is milk or water. You'll form a single, or you'll form what you call a uniform solution. Now you're saying that miscible liquid mixtures are formed when liquids completely dissolve in each other in any proportion. In whatever proportions you mix, they're going to dissolve completely in each other to give that homogeneous solution. So what you will have formed at that point is what you call miscible liquid mixture. Or these are, one can say these are formed of liquids that completely dissolve in each other in any proportion to give a homogeneous solution. Now, these miscible liquids are of two types also. Miscible liquids can be categorized into two, and they can either be ideal solutions or they can be non-ideal solutions. And we are going to look at one by one. We are going to first look at ideal solutions, then after we look at non-ideal solutions. So allow me straight to go to ideal solutions. So we need to first define what an ideal solution is. And an ideal solution is going to be defined as ideal solution is a solution in which the forces of attraction between unlike molecules of the components are equal in magnitude to those between the like molecules of the pure and separate components. Ideal solution is a solution in which the forces of attraction between unlike molecules of the components are equal in magnitude to those between the like molecules of pure and separate components. What do I mean? The forces of attraction, for example, if I have components A and B, the forces of attraction between the unlike molecules, when I say unlike molecules, I mean AB. So the forces of attraction between AB are equal in magnitude, okay, to those between the like molecules. The like molecules AA or BB. That is what we are trying to mean. The forces of attraction between the like molecules, okay, is equal to the forces of attraction between the unlike molecules. So that is what we are trying to mean when we talk about an ideal solution. Now, another thing that we should know about ideal solutions, after this, you should note this definition with a lot of care. So after knowing what an ideal solution is, we go ahead to note that when an ideal solution is being formed, okay, there is no change in volume or heat, and this solution obeys Raoult's law. So what we need also to note is that this solution obeys Raoult's law. We are going to look at what Raoult's law states as, okay? Now, we need to note maybe some examples of the ideal solutions, examples of these ideal solutions, examples of ideal solutions. The examples include benzene and methylbenzene. Of course, we are talking about its mixture, benzene and methylbenzene mixture. 2, we talk about hexane and heptane mixture. Hexane and heptane mixture. Also, this mixture forms an ideal solution. Then we have methanol and water. Then we have propan 1-ol and propan 2-ol. We've got heptane and octane. Okay. We've got very many. Ethoxybenzene. No. We've got other solutions like chlorobenzene and bromobenzene, bromoethane and iodoethane, and very many others. So after knowing the examples, we need to know the characteristics or the properties of an ideal solution. Properties of an ideal solution. 1, the number 1 property of an ideal solution is that from the definition we get a property, the forces of attraction between molecules of the unlike components are equal in magnitude, to those between like molecules of the components in their pure and separate state. 2, this is what we got, or we have got this definition. Rather, we've got this property in the definition. Then, when an ideal solution is being formed, there is no heat change. So we shall say there is no heat change. There is no heat change when such a solution is formed. Another one, still, the total volume of the solution, is equal to the sum of the volumes is equal to the sum of volumes of the individual components. The total volume of the solution is equal to the sum of the volumes of the individual components. If you want to get the total volume of the solution, you will sum the volumes of each component. You get the total. Then lastly, the solution obeys Rod's law under all conditions. The solution obeys Rod's law under all solutions. So these are the properties that you need to know about an ideal solution. One, you get it from the definition. Two, there is no heat change when such solution is being made. Three, the total volume of the solution is equal to the sum of individual volumes of components. Then lastly, the solution obeys Rod's law under all conditions. So we've seen Rod's law, Rod's law, Rod's law. Let's see what Rod's law is. How does it state? So here we are going to say Rod's law, Rod's law of vapor pressures. So we want to state this Rod's law of vapor pressures. Now, this law states that the vapor pressure of a component, the vapor pressure of a component of an ideal solution at a particular temperature is equal to or is the product is equal to the product or is the product of its mole fraction and the vapor pressure it exerts, the vapor pressure it exerts in its pure state at that temperature. The vapor pressure of a component of an ideal solution at a particular temperature is the product of its mole fraction and the vapor pressure it exerts in its pure state at that temperature. All right? Meaning if you have component A in an ideal solution maybe can have two components, A and B, but to get the vapor pressure of maybe component A in that ideal solution, it will be equal to the product of its mole fraction. We shall see how we get the mole fraction and the vapor pressure it exerts in its pure state. All right. So in other words, from this law, remember it is a law. So when you're stating it, you do not need to change any meaning of anything. All right. You do not need to change any of the highlighted parts there. Now, the total vapor pressure of this system or the vapor pressure of the solution of this ideal solution will be depending on the composition of the mixture, and the partial vapor pressure of each component in the mixture is calculated using Daltons law. Let's consider an ideal solution of liquids composed of liquids A and B, where vapor pressure of A, let me call it pure A, because in our definition or in our law, we have vapor pressure it exerts in its pure state. So vapor pressure of pure A is P A dot, and that of pure B is PB dot. So we are having, while the mole fraction of A and B, let me call them the mole fractions of A and B, are XA, mole fraction of A is XA, and XB, since I'm talking about two, I will say respectively. Now, I have assumed all these basing on the law that I've stated, because in my law I have that the vapor pressure of a component of an ideal solution at a particular temperature is the product of its small fraction and the vapor pressure it exerts in its pure state. So that's why I've said that if I consider an ideal solution composed of liquids A and B, where the vapor pressure of pure A is PA dot and pure B is PB dot, while the mole fraction of A and B are XA and XB, then from Daltons law, okay, from Daltons law, it means that the partial vapor pressure of A, right? Actually here in our law, let's say the partial vapor pressure, the term vapor pressure is not because here you have the vapor pressures already. Okay, so let's say the partial vapor pressure. So from Daltons law, the partial vapor pressure of A, partial vapor pressure of A, which I can call PA, partial vapor pressure of A, is equal to, remember we said that the partial vapor pressure is the product of its mole fraction. So it will be the mole fraction of A and the vapor pressure it exerts in its pure state. So the vapor pressure it exerts in the pure state is P dot. So it is XA PA dot. Still from Daltons law, the partial vapor pressure of B, that is PB, is going to be equal to mole fraction of B times the vapor pressure of B, which it exerts in its pure state. So this is how we can state Daltons law. Even from the formula, you can state Daltons law. The partial vapor pressure of a component in an ideal solution is the product of its mole fraction and the vapor pressure it exerts in its pure state. The partial vapor pressure, that is how I have edited my law. The partial vapor pressure, I emphasize the partial vapor pressure. Now it means that to get the total vapor pressure, okay, to get the total partial vapor pressure, P total, will always be equal to the partial pressure of A plus the partial vapor pressure of B. But the partial vapor pressure of A is XA PA in pure state plus of B, XB, PB in its pure state. Now, you need to note that mole fraction, the mole fraction of A, this one should be noted with a lot of concern. The mole fraction of A plus the mole fraction of B should be equal to 1, or if given in percentage, should be equal to 100%. Now with this one, we can calculate very, very well. Can calculate very, very well. So, allow me go to let me derive a simple relationship between Rolle's law and then Dalton's law. Okay, so that is what we are going now to talk about. Now, relationship between Dalton's law and Rolle's law. Now, but we've been talking about partial vapor pressure, partial vapor pressure, partial vapor pressure. Now, in the year it was 1801, there was a man called Dalton. Dalton came up with a law of partial pressure, which states that for him, it was like in a mixture of gases. It was talked about gases. It was like in a mixture of gases which do not react chemically. The total vapor pressure or the total pressure is the sum of the partial pressures of the components. But anyway, we know, since we're talking about equilibrium, we know that the composition of the vapor in equilibrium with the solution can be calculated specifically by applying Dalton's law of partial pressures. All right. So this relationship is going to enable us easily calculate the composition of the vapor. So now, by applying Dalton's law, which states that the total pressure is the sum of the partial pressures of the components, but still, we need to know that for component A, the partial pressure of A is equal to the mole fraction of A in vapor phase times the total partial pressure. Okay, so that is for A. This is according to Dalton. Okay, that is according to Dalton. Now, for Dalton's law, the partial pressure of each component is given as the product of their or of its mole fraction and the total partial pressure or the total pressure. So from Dalton's law, PA is equals to XA in vapor, the mole fraction, times the total pressure. Even the same applies for PB, that is for Dalton. But for Rolle's law, it is that PA is equal to mole fraction of A times its partial pressure times its vapor pressure, in its pure state. This is equation 2. And this is according to Rolle. Now, comparing this, I need you to know this very well, that for Daltons, the partial pressure of a component is equal to its mole fraction times its total pressure. Now, these equations, since they are all talking about the partial pressures of A, it means that since this is equal to this, then this is also equal to this, meaning that the XA vapor PT, P total, is equals to mole fraction of A times its vapor pressure in pure state. Now, if we need the composition of vapor, I will say hence, the composition of vapor XA in vapor phase would be equaling to mole fraction of A times partial pressure of A out of total partial pressures. So in other words, to calculate the composition in vapor phase or the vapor composition, the composition of vapor, we need to first get the total partial pressure. So by using Dalton's law, we shall be calculating PT, then by applying Dalton's law, we can calculate the composition of vapor. So we are going to look at examples of these calculations in our next video. So in our next video, we're going to look at the application of what we have derived, or of these expressions that we've talked about. See you there.